Hey everybody, welcome to this week's recording on our assignment for building a table 1. As I mentioned in the actual assignment prompt, I honestly think that this is one of the most underutilized and kind of underappreciated skills that someone in any kind of scientific research really kind of takes for granted until they need to start using it on a fairly frequent basis. So this is kind of why I decided in past semesters that I've taught this course, this has just been clumped into either week 3 or week 4's actual content. But when I was redesigning the course for this semester, I decided that this was something that kind of deserved its own week and its own dedicated time to learning and actually working through this skill. So that way, you can see the ins and outs of how this stuff is actually done and put together. So we will hop right into building a table 1. The first thing we need to do, though, is take a look at your assignment. Let's get that over here. So we will be building a table 1, and you will have, I posted a 6-page document for you to look through. It's kind of briefly covers on how table 1s are put together, how to analyze the pieces of data that you have, so on and so forth, to actually build and run the necessary statistical tests to build your table 1. But this week, or for this assignment, I actually would like you to build that table 1. So what we will be doing is building a table 1 for comparing patients who received the neuromesh and the patients who did not. Along with building the table 1, it's asking you to write a short narrative. This would be basically the paragraph that describes the patient population. The patient population who received the neuromesh and the patient population who didn't, and comparing them together. This is, of course, something that you have to wait until you actually have gone through all the statistical tests to actually write and put together. This week, too, for anyone that would like to take on a small little added challenge, I added an extra credit component to build an additional table 1 and write a short narrative comparing patients who have experienced a severe stroke, which is a SASI score of greater than or equal to 7, against those who did not. I give you a little hint here on what you should do to build a new binary variable, so that way you can very easily separate the patient population. Like we will do something very similar to this in this recording, dealing with the 2 race variables and kind of separating and combining them together at the same time. All right, so let's switch over to SPSS now that we have that part taken care of, and open your Stroke MedDev Inc. data that I have posted for you. One thing, like I've mentioned in all of the previous recordings, this recording here only is using a subset of your data. So I have just under 28,000 cases in my data set, whereas the data set that you have has roughly 74 or 78,000 patient encounters in it for you to analyze. Right. So, right off the bat, what we should do is take a look just at our data that we have, all of the different variables, as well as the data that is comprising some of these variables. Data that are strings, which is indicated by this little A here, and you have it under the diagnosis 1 along with the race 2 variable. These for SPSS are kind of difficult to work with, but luckily enough we have another race indicator Here, that is a numeric variable, which will be much more easy to deal with. So what we will end up doing is likely taking out this race2 variable, but we will look at that in a moment. The other couple things that we have in this data set that kind of catch my attention is the disposition of the patient, DISP UBO4. So this is the UBO4 indicator for the discharge disposition of the patient. This is something that we will exclude from this analysis. When you run a frequency analysis against this variable, you'll see that there is a very wide range of patient dispositions, and they are all not contained within this data set. And we will see that the disposition of the patient does not play into the question that we're being asked. So this is a variable that we will be able to get rid of. That will also include the DRG, which is a diagnostic related group. That is effect on the discharge date, is another variable that we will be able to remove. These are stroke patients, so we are only looking at the patients that are receiving and the patients that didn't receive the neuromesh. We're not particularly concerned with their DRG or their diagnosis. We have more of an interest in the history of stroke, in the history of acute ischemic stroke variables that we will deal with, and those in this situation are more important than the DRG and the primary diagnosis. The other two variables that catch my attention in this data set are phenotype 1 and phenotype 2. This, along with the other ones that I mentioned, are used primarily for either categorizing or categorizing patients, grouping them together, or to striate and separate the data sets into two different groups. In this situation, we also do not need the patient phenotypes. We have not been given a definition of what these phenotypes are. If you recall, in last week's assignment, I do mention that the phenotype 2 is the patient phenotype for selection of the patient selection for the neuromesh. But in comparing the ones that received it and the ones that don't, we've already determined that they are all in phenotype 2 from last week. But as I just mentioned, in this week's assignment, we haven't been given an explicit definition of what phenotype 1 or phenotype 2 is. So again, that is a categorical variable that we can exclude from our analysis. All right, so saying all of that, I'm going to switch over to my variable view and start removing some of my variables that I mentioned. So I mentioned that we do not need the patient disposition, and we also do not need the DRG, nor do we need the patient's primary diagnosis. So this one can also be selected for removal. For right now, we're going to leave the two race variables. You will see why in a moment. Which ones were the other ones? All right. The other ones I mentioned are the two phenotype variables. These ones can also be removed. So starting with these, I will select those and then do a right click and then do clear. And that will go ahead and remove those variables from my list. So now I mentioned that I need to deal with the two race variables because SPSS typically doesn't like dealing with strings unless they are a numeric variable that is using labels, which is a much nicer and cleaner way to switch back and forth between a string and a numeric value. So to start and to figure out how we'll deal with these two, I'm just going to run a quick frequency analysis against them. So that way I can see what these two variables are comprised of. Statistics, I'm not particularly interested in running anything of these, nor do I need any charts because I'm just purely interested in the composition or the frequency composition, I should say, of these two race variables. So I'll add them in and click OK. So for the first variable, that is just race, I have values 1 through 6. And then my race descriptor, the one that it was containing black, white, or other, I'm seeing only 3 with a 247 missing values and 247 missing values up here. What you can do to start with, and this likely won't work in every situation, but conveniently does in this one, I'm able to match to see that my race descriptor of white contains 20,319 patients, and my patient race value of 1 also has 20,319, and patient race value 2, 3,541, and then down here in the black race descriptor, I have 3,541 as well. Just to be sure and to cross all of my T's here, my missing system values also match, but I would just want to do a quick thing here. Values 4, 5, and 6 is 189, 29, and 343. It's 561. And value 3, don't forget that one, 3270. That much better. 3,831. I have 3,831 and other here. So that tells me that in my patient race numeric variable, that the value of 1 is white, the value of 2 is black, and then the values of 3, 4, 5, and 6 make up the other descriptor, and my 247 missing systems values match on both variables. So this all checks out, and this is really good, and will make our lives quite a bit easier in our next step here. So in the past weeks, we have done, or we have used this recode into different variable. So we're going to use this function again, and the variable that I am going to use to recode is the numeric race variable. So I will select that one from the list, move it over to here because I can only use numeric variables. So I'm not able to do anything with the race string. And then my new variable name is going to be race category. And we'll choose change to apply that. So that way SPSS will recode all of the values from race into a new category, new variable that it will create called race cat. All right. So to match the values from one variable to another, you're going to use this old and new variable. And we have already determined that 1 is white, so I am going to leave 1 equals 1. And we have determined that 2 equals black, so 2 equals 2. And then for the next one, because I'm going to use the remainder of my numeric values here for other, I'm just going to do a range from 3 to 6. And my new variable value will be 3. And I also want SPSS to leave the 247 missing system values alone. So I will choose system missing to system missing. So that way, again, SPSS will just leave any of the blank values alone. So just to review, my old race value is 1, and my new race cat value is 1, 2 is 2, and race values 3 through 6 will equal race cat 3, and all of my missing variables will stay as is. Right, so we'll click continue, and we will click continue one more time. And you see the recode command has been entered into the output, and I have my new race cat variable in my variable view. So I am just going to give it a quick label, which is recoded race. And I'm going to remove the decimal points because those are fairly irritating and not necessary. And now I can go ahead and remove my 2 race variables because I do not need them anymore. Great. Okay. So now that we have all of the variables that we want, aged, died during hospitalization, gender, length of stay, days until readmission, received the neuromesh, skilled nursing facility, history of stroke, acute ischemic stroke, TPA, SASE, Charlson, charges, cost, and race. This all looks good to me, so I will leave everything from this point as is. And just switch over to my data view to make sure that everything looks okay, nothing is kind of skewed or nothing has changed that I wasn't expecting, so that all looks fine as well. Great. So the first thing that I asked to do in the building the table 1 document is to run a couple of simple analyses on the data that you're given. And it's easiest to start with the continuous variables. The first thing that we want to look at and understand is, are any of the continuous variables that we have normally distributed? So the easiest way to do that, or the fastest way to do that with multiple, is to use the descriptive statistics and explore function in SPSS. And that way I can just go ahead and add in all of my continuous variables. You'll see here that I did select SASE score as a continuous variable, even though it is currently marked as a nominal variable or nominal typed variable. For the purposes of this assignment, and as we go further through this recording, you'll see that we will change it to a scale variable. The SASE score does act as a continuous variable, and it is not a nominal or ordinal variable, even though it is marked that way in the dataset. Until we get to an analysis a little bit later on, leaving it as nominal is perfectly fine. Nothing will happen. SPSS will continue to treat it as individual values, and your analysis won't be affected. All right, so let's pile all of those into the dependent list. And in my statistics here, I do not need any of the outliers or percentiles. I am interested in the 95% confidence interval, so I am going to leave that. In my plots here, I am interested in seeing a histogram as well as viewing the normality plots with tests. So these are the QQ plots. We looked at them, I believe, in week 2 or last week in week 3. The QQ plots is just another way of determining normality, and we will take a look at those in a minute when they come up. All right. So don't need to worry about anything here. We're not doing any bootstrapping, so that's perfectly fine. I'm interested in seeing both, of course, so we'll leave that there and click OK. So this will likely take a minute or so to actually run. Excellent. So the first thing I get in my Explore analysis is the case processing summary table. This is showing me that I have 27,213 valid items for analysis, 725 missing values for the total of 27,938. So in my Explore analysis, SPSS is only going to select the n number of valid cases in my data set to run. So let's take a look at the age piece, which is the first part. It gives us the mean, median, and standard deviation, as well as two pieces of information, the skewness and kurtosis. We talked about these in last week's recording, and skewness and kurtosis are two statistics that you are able to use to also determine normalcy. As skewness and kurtosis approach a value of 0, is approaching a normal distribution of data. So saying that a set of data has a skewness and kurtosis of 0 means that the data is perfectly bell-shaped symmetrical and is perfectly normally distributed. We'll see in the table under this one, in the tests of normalcy, that the skewness and kurtosis is put through a statistical test. Just scroll down here, called the Kolmogorov-Smirnov test. And this is also another test of normalcy. The way to interpret this table here is this sig column, or the significance. And this one is interpreted a little bit different than sig columns in other types of analyses. If the significance value is, I always get this mixed up, so I'm going to get it right the first time. If the significance value is less than 0.05, the variable is not normally distributed. So I have, my significance value is 0.000, so they are all less than 0.05, indicating that all of my continuous variables are not normally distributed. And that is also confirmed by looking at the skewness and kurtosis. My kurtosis of patient cost is 660. That is very far from 0. The only one that was kind of even close that I would look at with a little bit more care is days until readmission, as well as age in years. So that's something that we can certainly do because we have our histograms. So the age histogram is almost normally distributed. One thing that we can do that is very helpful, if you double click in your histogram, you will get your chart editor. And one thing that you can do is add a normal bell to your chart editor. And that is done by choosing Elements and choosing the Show Distribution Curve. And normal is the first curve, so there's nothing that you'll need to do because normal will already be selected, so you just choose Close. And now we have a normal distribution bell to see how our histogram will fit into a normal distribution of this data. We can see that the age is slightly skewed, but not terribly skewed. So this is where I would go back to the Kolmogorov-Smirnov test to see the sig value of this. just to check and confirm that it is or is not normally distributed. From this test, I do know that my age is not normally distributed, and that is also confirmed by my QQ plot. This dark line, the black line that goes through the middle of my QQ plot, is a line of perfect normalcy, and the plots you see are the two quartile ranges, quartile 1 and quartile 3, that are both plotted against each other, which is how you get a QQ plot. And if this data was perfectly normal, you would see all of those individual plots fall right along this normalcy line. So again, that it does not do. So we can confirm that age is not normally distributed. And the other one that I did want to look at just to confirm was days until readmission, because these two are fairly close to 0. So let's go down to length of stay, days until readmission. So I have a fairly uniform distribution, with the exception of this one spike that is fairly perfectly in the middle of my data set. This is something that I would probably look at in a little bit more detail to see why I have a spike. It's not going to tell me what these values are, but that's fine. But I do have a mean of 163. So why I have a spike in my days until readmission at about 160 to 180-ish days. Again, I will go ahead and add my normal distribution curve so that way I can just see. You see how we don't have a very tall bell like we would expect. It's a more flat shape. So that's also indicative of some kind of data error or outliers that you may want to go look at to see what is causing this from your primary data source. But looking at this and my Kolmogorov-Smirnov for data until readmission, I do know that this variable is not normally distributed in my data set. And then we can scroll through. We have the SASE here. You'll see how the plots fall off the side of the line and is not indicative of a normal distribution. And we can see very clearly here that Charleston score is not normally distributed. Again there. And it is very rare that bill charges or total patient costs in any data set are normally distributed. They're usually very skewed, and that's something that you can almost take for granted in whatever data set you happen to be given. Right. So now that we have kind of investigated the continuous variables, let's go ahead and do the similar thing to our categorical variables. And we will do that just by running a quick frequency analysis on the categorical variables that I'm interested in, with the obvious, sorry, not so obvious, but will be obvious shortly, the SASE score. I'll run the frequency analysis on it now just to kind of show you. But again, like I mentioned, this will be a variable that we will switch to a scale variable shortly. At this point, I'm not particularly concerned with any of these statistics, nor am I concerned with any of the charts that can be produced from a frequency analysis. So I'm just going to run a simple frequency table. So looking at my statistic table here, I have 27,938 valid observations for every variable except for the race indicator, which I had already expected. So that is good. And if we just go through quickly and look at the different categorical variables, died during hospitalization, our values are alive at discharge, and died during hospitalization. We have a very low number of patients who died during their hospitalization, which is good. That's something that we would hope for. We have a nice, almost even mix of patient genders, so that is also good. We are aware that this data set is from a clinical trial, so the number of patients who actually received the trial device, the NeuroMesh, is fairly low in comparison to the patients who didn't. So again, this is something that we would kind of expect to happen. Patient discharging to skilled nursing facilities. We have a much higher number of patients who are not discharged to a skilled nursing facility in comparison to the patients who are. One thing that we could have done to see where these 22,832 patients go would have been to leave the disposition UBO4 variable in here. That would have given us some kind of indication or some kind of hint as to where the patient would have been disposed to after discharge. So a couple other ones, patient history of stroke. So this is a very interesting finding here. This is telling us that all 27,938 patients in my data set have a history of stroke. So this is something to keep in mind for your analysis when you are writing, but something to keep in mind because it is a constant. Patient history of stroke variable is a variable that you also can exclude from your analysis going forward. The last ones that we have here are patient history of acute ischemic stroke. We have almost an even distribution of patients who have and patients who haven't, so that is interesting. TPA administered en route to the hospital. There was only just about 1,100 patients who received TPA en route in comparison to the 26,000 patients who did not receive TPA. If your hospital has TPA treatment protocols, this would be something that may warrant some further investigation on why TPA wasn't administered en route. There could be a very good reason that your EMT facility in the city does not have the capability to administer TPA. That's wild speculation, but something that would most likely warrant some further investigation. All right. Next up, then we have the SASE score. We can see here our patients range from a value of 0 all the way to 36. This, like I mentioned, is something that we will look as more of a continuous variable. Even though it is an index score, it will make and function, or I should say it does function closer to a scale than it does a nominal variable. And the last one here, the recoded race indicator. We've seen this frequency table before. We have the white race, black race, and other race, as well as the 247 missing race entries. All right, so continuing on, sorry about that, I had to pause the recording for a quick moment. We have looked at our continuous variables, we've looked at our categorical variables, and if we were building a table 1 to explain the entire population, we could actually stop here because we have all the information that we need. But in this situation, in building a comparative table 1, we do need to keep going. So to revisit the assignment, the question that we are trying to answer is what are the differences between patients who have received the NeuroMesh and the patients that did not, and displaying that in a tabular format, such as a table 1. So one advantage that we have doing this is that the mesh variable here is already a binary categorical variable, meaning that the only values that it has is 0 or 1. So that makes our lives a lot easier, as we saw with dealing with that race variable. If it was still in a phenotype or in a DRG or in a primary diagnosis, we would need some kind of way to be able to extrapolate that data out and build it into a binary variable such as this. But this information has already been provided to you. So like I said, it makes our lives in this situation a lot easier. So the first step that I like to do when I get to this point is to run the means tests. So that is going to look at the means, a comparative mean of age, length of stay, readmission, all of our continuous variables split based on our mesh variable here. So I will do that by going to Analyze, Compare Means, and then Means. And I'm going to go ahead and select my continuous variables and place them up in my dependent list. And then my independent variable in this situation is going to be my neuromesh, and I'm going to add that down here. So in this situation, the layer field, which is the independent variable, is basically acting as an if statement. So what is, if I were to look at this and just looking at age, what is the mean age of patients if they receive the neuromesh? So this analysis tool is going to tell me the mean of patients who did receive the neuromesh and the mean age of patients who did not receive the neuromesh. In looking at some of my options here, the only thing I'm particularly interested in is the mean value and the standard deviation, because these are the two pieces of information that I need to go into my table 1. So I will not make any changes here. I'm just going to simply click Continue and click OK. So what I have here in this box right down here are the receive neuromesh 0 and receive neuromesh 1. So the 0 is the number of patients who did, I'm sorry, not the number, patients who did not receive the neuromesh and patients who did receive the neuromesh. I can make this bigger. No, that's okay. So for my patients who did receive the neuromesh, so the value neuromesh 1, my mean age is 58.45 years with a standard deviation of 6.35. They have a length of stay of 4.11 days with a standard deviation of 5.6 days. They have a mean number of days until readmission of 160.1 and the standard deviation of 80.63. These patients have a SASI score or SASI index of 3.1 with a standard deviation of 4.5, so on and so forth. You see how this is read. And then looking at the other side of the table here, patients who did not receive the neuromesh, they have a mean age of 72.3 years with a standard deviation of 13.5, an average length of stay of 5.95 days, standard deviation of 8.6 days, so on and so forth again. So you have the numerical data that you need to build your table 1 in terms of the values, so the mean and the standard deviation to list. but you don't have from this table a comparison significance or a comparative p-value to say, is the difference in patients who did not receive the neuromesh of 72.3 years of age and the patients who did receive the neuromesh of 58.45 years, is this difference significant between the two population groups? And that is something that is determined by a test called the Mann-Whitney-U test. And because we have already determined that all of our continuous variables are non-normally distributed, we only have to run this one test for all of our continuous variables. If we had any variables that were continuous variables that were normally distributed, we would have to run a independent sample t-test. But again, like I mentioned, because none of these are normally distributed, that's not something that we have to do in this situation here. So to run the Mann-Whitney-U test, that will be under Analyze and Non-Parametric. And let's choose the Independent Samples Testing. So to set up a Mann-Whitney-U test, the first thing that we're going to do is do a custom analysis, because this will allow us in the Setting tab when we get there to choose the test that we want and stop SPSS from running every test it thinks that you may want. It's easier to limit it down to start with. So switching over to the Field tab, we're going to go ahead and select our continuous variables. So we have age, length of stay, days until readmission. The SASE score will act as a continuous variable, Charlson, bill charges, and patient cost. And let's move them over to our test field, and you will get this error saying that nominal fields cannot be placed in this list. If you remember, I mentioned earlier in the recording that SPSS will deal with the SASE index score being a continuous variable until we need to test a comparative, the comparison between the two. This is because the Mann-Whitney-U non-parametric test is used for continuous variables, not for categorical or nominal variables. So what we will do is click OK on that. We're just going to cancel our non-parametric setup here and switch back to our variable view. Locate my SASE score. Why all of these are so very expanded. And select my SASE score, and I'm just going to change the measure from nominal to scale. All right, so let's go ahead and set up that test again. And we will choose a custom analysis. And we see now that the SASE variable is has the ruler, so now it's been switched to scale. So now we can just go ahead and click this button here to select all of the continuous variables, add them into our test field, and then go ahead and select our grouping variable, which is our neuromesh variable. So let's go over to the Setting tab next. This is, selecting the custom analysis here will allow us to select this custom test option here. And the only one that we're interested in this situation, like I mentioned, is the Mann-Whitney-U two-sample test. You do not need to worry about any of the other options because the standard significance level is 0.05. So this isn't something that we need to change because we're not doing a 0.01 or a 0.1 level of significance. And we will let, even though for these continuous variables, we don't have any missing values, but we do have the option if we did have missing values, if they wanted to be included or excluded. Right. So all of this looks good. Let's go ahead and hit run. This will also take a minute to run through, and then we will get our result. So the independent sample Mann-Whitney U-test, the output looks a little bit different, as I mentioned last week, than what we've kind of seen and dealt with before. This output will give you a null hypothesis. So let's take a look at the first one. The distribution of age in years at admission is the same across categories of received neuromesh. So what this is basically saying is that the distribution of age in years at admission is the same between the patients who received the neuromesh and the patients who did not receive the neuromesh. And it lists the test that SPS has run, along with the test's level of significance, or the test p-value, which is 0.000. 0.000 is less than 0.05. So we can say that this result is significant, and the output is to reject the null hypothesis. So by rejecting the null hypothesis, you are saying that the distribution of age in years at admission is not the same across patients who received the neuromesh and the patients who did not receive the neuromesh. Basically saying that there is a significant difference between patients who did and patients who did not receive the neuromesh. So that is the same outcome for length of stay, the SASE score, the Charlson score, bill charges, and the total patient cost. Interestingly enough, number 3 here, the distribution of days until readmission, is the same for patients who did receive the neuromesh and patients who did not receive the neuromesh. The p-value of this test is 0.694. Which is far larger than 0.05. So in this situation, we actually retain the null hypothesis, meaning that the difference between the number of days until readmissions for patients who received the neuromesh and patients who did not receive the neuromesh, the difference between those two are not significant in comparison. Cool. So now we've addressed, at this point, all of the continuous variables. The next thing that we need to look at are our categorical variables, in determining if there are any differences in those for patients who received the neuromesh and for the patients that did not. And the way that we will do that is by running something called the chi-square test. And the chi-square test is in a spot that we have already been before, which is in our crosstabs. Let's go ahead and go to Analyze, Descriptive Statistics, and Crosstabs. And I'm going to pile in my categorical variables of died, gender, skilled nursing facility, history of stroke, acute ischemic stroke, TPA, along with my race. As I mentioned earlier, we don't really particularly need this history of stroke variable since the value is 1. I am just going to include it in here, included in this analysis to show you what will happen in terms of the output of the chi-square test for a constant variable. Let's put all of those up there in the rows. And in the columns, I'm going to go and select my received neuromesh. Put that up in here. And to enable or turn on that chi-square test, I'm going to choose my statistics option and pick chi-square. All of these other tests, the lambda or the eta, kappa, we're not interested in any of these. They are kind of outside of the scope of what we will cover in the duration of this class. If you're interested in what these other tests for categorical variables are, you're more than welcome to dig into them a little bit more on your own. If you have any questions, feel free, shoot me a message and I'm more than happy to talk about them. Right. So I have my chi-square. I'll click continue to make sure that runs. The other thing that I need to add to this piece of the analysis is the percentages. And that will be in my cells option here. So I have a row percentage, a column percentage, as well as my total percentages. The one that I am interested in enabling in this situation is going to be my column percentages. And you'll see why in a second, but my column percentage will give me the percent of patients who die during hospitalization by the column variable here. So let me just run that and it will make more sense in a second. So as I mentioned, I have the first one is died during hospitalization by receiving the neuromesh. So I have died during hospitalization and the neuromesh variables here. My percentages are calculating in the column. So basically I'm saying what is the percentage of patients who died within receiving the neuromesh. So the number, I have 1,066 patients who did not receive the neuromesh that died, which is 3.8%. And then I have only 2 patients who received the neuromesh that died during hospitalization, which is 2% here. So what this is saying is that the p-value of my Pearson chi-square for the comparison of patients who died during hospitalization that received the neuromesh to the patients who received the neuromesh that died during hospitalization is 0.333, which is greater than 0.05, meaning that the difference between the two groups is not significant. So let's scroll down to the next one here, patient gender. My Pearson chi-square is 0.31. So again, I have another variable here that the difference between male and female in receiving, the difference in female patients who received the neuromesh and the patients who did not receive the neuromesh is not significant. All right, discharge to skilled nursing facility. All right, here. So the p-value for the Pearson chi-square test for patients discharged to a nursing facility is 0.001. So this p-value is telling me that the difference in the number of patients who were discharged to a skilled nursing facility that received the neuromesh and the patients who did not receive the neuromesh, the difference between those two groups is something significant. And this here is the part I wanted to point out to you, patient history of stroke. You'll see here in the chi-square test, no statistics are computed because patient history of stroke is a constant. So this is basically saying that I only have one value for patient history of stroke, so I can't actually run or perform a Pearson chi-square analysis because I do not have two groups here to compare the difference between. All right. And last but not least, the one other part of Pearson chi-square I do want to point out, because in this situation we are looking at the difference between receiving and not receiving the neuromesh versus the difference between race 1 and race 2, race 1 and race 3, race 2 and race 3, we're only looking at receiving the neuromesh and not receiving the neuromesh. We are able to run the chi-square because chi-square will run against one group versus another. versus if I was concerned with the differences between these three groups and receiving a neuromesh and not receiving the neuromesh, I would have to run a multivariable ANOVA to be able to determine that. But in our situation here, the Pearson chi-square p-value is 0.932. So we can say that there is no significant difference in race for patients that did receive the neuromesh and patients that did not receive the neuromesh. And at this point, now you have all of the information that you need to be able to populate your table 1. Let me bring over a different table 1 real quick. So this is a table 1. No good. So this is a table 1 from a different year for the patients being discharged to a skilled nursing facility and patients who were not in terms of stroke care. And you can see here how, especially for race, I only have one calculated p-value because it is the difference between patients who were discharged to a SNF versus patients who were not discharged, and is not looking at the differences between the 4 race groups. So when you're building your table 1, you're going to want to just put your p-value for race in this section alone, and then go ahead and list your frequency of each race as well as the percentage that those go ahead and make up. In terms of building your table 1, whenever you are listing a mean in a table 1, you'll also want to list its standard deviation. When you're talking about a categorical variable, you will list its frequency followed by its percentage. And one other piece of information to keep in mind, when you are talking about large currency means, so anything over $999, you will drop and round all of the decimal points. So here, I have total charges mean. I know, interpreting in table 1, that total charges is a dollar amount, so I also do not need a dollar sign. But as I mentioned, it is over $999, so I went and dropped the decimals and the cents off of my $86,388 total mean charge for patients that were discharged to a SNF. And again, being continuous variables, I have my standard deviation as the number that is in parentheses there. And then I have a column with my p-values. So all of these pieces together are what make up a table 1. As I mentioned, you have now calculated or analyzed or will receive from your analysis all of the pieces of information that you need. The table 1 in the building a table 1 document, as I mentioned, is from a different data set from a different year this course was taught. So I received an email about this admitted during the weekend variable. This isn't something that appears in your data set. I gave the example table 1 in that building a table 1 document just as an example, so that way you can see how they're comprised and put together with all the different columns and pieces of information that you need. You will use the variable names or the variable labels here. You should by now be able to interpret working with this data. You know that TOTCHG is total bill charges, so you'll write an appropriate label for that variable in your table 1 and not, you're not going to put, because nobody knows when they're reading your Table 1 are reading the publication, they may not know what tote charge means. So that should cover everything. In terms of the building your Table 1, I will take a copy or a draft of your Table 1 up until Friday. You can go ahead and submit it using the link that's in Blackboard, and I will review it and provide comments back to you, so that way you can go and make any changes that you would like, before you submit that Table 1 for final grading. But as I just want to mention that you do have to submit a draft by end of day, so 11:59 p.m. Eastern Standard Time on Friday. So that way I can rip through all of them on Saturday, get them back to you, and you can go ahead and make any changes or corrections and then submit your final draft on Sunday. So other than that, that should cover everything for building a Table 1. As I mentioned, this is a very important skill, and is something that I try and get across in this class. I feel as if it's something that's very important, and it gives you an appreciation kind of for the amount of work that goes into building something as simple as a Table 1 of patient information or patient comparisons. Just kind of look back and think back to the number of different scientific papers that you've read over however many years that you've been in school or working in your career. The Table 1 is something that you've paid attention to, but you've never really sat and, for lack of a better way to put it, sat there and appreciated the amount of work that goes into building this table of data. So hopefully by the end of this module here, you will have a different sense of appreciation for a Table 1 in a scientific paper. It's something that is a tool or a resource that I'm hoping to leave behind in your toolbox for your careers going forward. So that's all I have for you this week. Enjoy, have fun. I think that this is one of my more favorite assignments to do. It's one of my more favorite assignments to write. If anyone has any questions, please feel free. Shoot me an email, let me know. I look forward to and I encourage you all to submit a draft, so that way I can look at it ahead of time. As with all of the other assignments, the assignment resubmission policy also applies here. So if you don't have time or you can't make the Friday deadline to get a draft of your Table 1 into me, and then you don't do so well or you don't understand it, and you get your grade back from the final draft, you still will have the opportunity to redo and resubmit your Table 1 for secondary grading after the fact. Right. So for the third time now, that wraps up the recording for this week. Any questions, please feel free and let me know. Other than that, we'll talk soon and enjoy the rest of your week.